Hey, my name is Andrew Lockhart, and I currently work at Drexel University College of Medicine under Simon Danner, and my poster is about control mechanisms for turning in a quadrupedal robot. So the main goals of this poster is to go over how different asymmetries can cause different types of turning in a robot. We use an in-house robot that is a quadruped that it has body bending capability so that the front half of the robot is able to bend compared to the hind, so that the hind limbs continue going forward as the front half of the robot is able to turn. And then lastly, we use a control mechanism that mimics rhythm generators within the spinal cord because ultimately we want to bring our computational models to reality through robotics, and this is just the first step. And this control mechanism is able to allow us to use robotics as a tool to study more about biology. So to give an overview of that controller, you can see it on the left side, where we have four different coupled oscillators that are going to mimic our rhythm generators within the spinal cord. Each one of these rhythm generators represents one of the limbs, the front left, the front right, the hind left, the hind right, and they're coupled together to give interlimb coordination. Each one of these rhythm generators is going to output a phase to a corresponding limb. We're going to use this color coding throughout the poster, where the front left limb is going to be represented by green, the front right blue, the hind right orange, and the hind left black. As phase is transmitted to each one of these limbs, they're going to step through our position controller that controls the trajectory of the limb, that's characterized by a step height, a stride length, and an angle that's not shown here that's going to control medial lateral movement. So as the phase is sent from the rhythm generators to the limb, we step through this trajectory over and over and over again. And then one last thing is we record different types of things from the limb to produce feedback to send back to the controller. So each one of these oscillators is going to control the movement and flexion, extension, transition of one limb, and the phasic output from these oscillators drives that position controller through its trajectory. So we model two types of feedback, and we choose these two types of feedback because they're most likely, or at least we think it's most likely, that they control the swing to stance transition in animals. And so this is modeled after prior animal literature. So we modeled the angle feedback and the ground reaction force. So to go into the angle feedback, you can see the front left limb here with an angle drawn here between the 0 point and where the limb is currently at. And you can see these arrows, which represent the amount of feedback that it's going to provide. So for hip shoulder hyperextension, it's going to cause a decrease in stance duration and advance to transition and swing. Basically meaning that if you're caught in hyperextension, it's going to push you into swing phase. So that's going to occur more at the beginning of stance. So if you just touch the ground but you're hyperextended, we're going to increase it to push you back into swing. And then on the other end, we're going to have this ground reaction force feedback, and it's going to have the opposite effect. So we have these two competing feedbacks where ground reaction force is going to record the loading of the limb, and it's going to prolong the stance phase and shorten the swing. And so this is actually going to decrease as we get further into swing and increase as we get further into stance. So at the beginning of stance, we have a shorter or at least impactful ground reaction force feedback, and at the end of stance we have a more impactful ground reaction force, because if you're at the end of the stance phase and your limb is not unloaded, it means the other limbs haven't caught up, and if you lift that limb that's carrying all the weight off the ground, you're going to fall. Unlike angle feedback, we actually model ground reaction force during swing phase, and so if you begin to touch the ground during swing phase, we're going to push you back into stance by increasing the frequency and adding and shifting the swing phase forward. And so all of this controller comes together to produce the full gait transition of animals, from walking to trotting to bounding to galloping. We're mostly going to focus in this poster on walking and trotting because it's the physical capabilities of our robot. But we're able to get both diagonal and lateral walk and then trot for a wide range of bifurcation parameter. So it's good to have this bifurcation parameter because there's only one parameter that's going to control the gait, which means that we can independently vary any other parameter, and it's not going to change the type of gait we get. So you can see here the transition from walk to trot. On the y-axis, you see each one of the limbs labeled right fore, right hind, left hind. The blocks are going to represent when the foot is on the ground. The blue background just represents a walk. The green background represents a trot. And you can see this transition from walk to trot, from these diagonals that are being created during walk to synchronization between the diagonals and trot. And you can see that better here in these normalized phase differences, where you can see that they slowly transition to where the diagonal limbs are synchronized and the alternate diagonal limbs are out of phase. And so the blue dots represent the right forelimb homolateral phase difference. The orange dots, the right hind limb homolog phase difference. The green dot's the left forelimb homolateral phase difference, and the black dot, the left hind limb reference limb. And so we use this left hind limb as the reference limb to calculate the phase difference between all of the limbs. And so you can see a zoomed in average of walking and trotting here. Something interesting to note is that recently our optimization has been using feedback to transition trot to look more like walk, which is why you don't see perfect synchronization of the diagonals, because it's trying to use our feedback to cause more limbs to be on the ground because it's more stable, because one of the things we optimize for is a decrease in rotation when we're walking straight. And then you can see these polar diagrams below that also represent and show the phase difference between each one of the limbs following the same color coordination for walking and trotting. But the main thing about this poster is we wanted to look at how different asymmetries and different types of turning are able to be produced. And so in this plot, we look at three types of body bending and medial lateral movement. So we have just regular body bending where the front limbs are going to be at a diagonal compared to the hind limbs. Front medial lateral movement that's going to step out to the side in the medial lateral direction, but only of the front limbs. And then we do front and hind limb, but we make them go in opposite directions for medial lateral movement. And we do this at half the angle as the others so that the angle difference between the hind and the fore stays the same so we can compare them. On the right side, you can see trajectories. And so we chose parameter values where the 1 over the radius is equal to 0.6. So you're able to compare more evenly between them. And so on the x-axis here, you can see the angle in degrees between the hind and the forelimbs. And on the y-axis, you see 1 over the radius. So as this value on the y-axis increases, you're making a sharper turn, meaning that the radius of the circle is getting smaller. And so you can see that it's perfectly symmetric down the center. And surprisingly, all three of these asymmetries cause similar types of turning. One thing to note here is that the bend here in body bending is actually caused to the front and the hind limbs hitting each other because the stride length in these was so long that as we bent the body, the hind limbs started interacting with the forelimbs. Next, we wanted to look at different types of asymmetries: duty factor, stride length, and frequency. And so duty factor is just how long the right or the left side is going to be on the ground compared to the other side. And so as we increase one side being on the ground longer, we decrease the other symmetrically. So you can see here we increase the right side, but also decrease the left side. So the left side's on for a shorter amount of time than the right. Stride length has a similar effect where the right side is increased and the left side is decreased. So the right side's taking a longer stride than the left side. And then lastly, frequency, you can see that the right side is taking more frequent steps than the left side. And then the only difference in this graph compared to the last is that the x values is actually going to be the log of the right over the left, where the right asymmetry value is going to be divided by the left, and we're going to take the log of that to give you the ratio. And so on the right side of the x-axis, we actually have the right side of the robot being a larger value than the left, and on the left side, the negative values here means that the left side, meaning like the duty factor or stride length, is longer on the left side than the right. And what we find from this plot is that duty factor turns towards the side with the longer duty factor, and we also see that asymmetric stride length turns towards the side with the shorter stride. And then lastly, we see that asymmetric frequency does not produce stable turning. And so you can see all these red dots here because the robot's beginning to shake or fall over, and it's not producing stable turning at all. So frequency really isn't a good way to cause turning. However, the other two asymmetries cause pretty similar turning. And then at these bends here, the robot begins to fall over or shake. And so the main conclusions from this poster is that left-right asymmetries of locomotor parameters results in turning. Body bending and medial lateral limb movement result in similar turning radii. How animals choose between these similar turning strategies is still a question and something that we're going to investigate further. And then different strategies allow for different limits of stable turning. So you're able to see that these different types of asymmetries compared to body bending are able to fall apart at different limits. And so going forward, we're actually going to do optimizations where we allow every type of parameter that causes turning and also different types of trot and speed, and plot how different types of turning is performed at different types of speed. And then we may also look into how that depends on different types of environment. But overall, this is just a stepping stone to my thesis work, where I'm going to be looking at our full genetically defined neuronal model that's hooked up to a torque-controlled motor to introduce afferent feedback to the system. And so this is just the first step in introducing our computational models of biology into the real world. If you have any questions, be sure to leave them in the comments and I'll get to them. Thank you.